Okay, hello and welcome to this session on planar, also known as two-dimensional motion analysis. Now, the purpose of this online session, this lecture, is to provide you with a theoretical basis for the more applied and practical aspect of motion analysis that you will be performing later in this module, i.e. collecting data for your assessment. So most of the content here you will perhaps hear again at some point, and all of it you will most certainly need to know and will apply in order to collect the data that you will be collecting. So let's begin then by stating a question, well, questions technically, but I've kind of mushed them together in one very poorly phrased question. Well, the idea of this is to give you a theoretical basis and theoretical knowledge of this topic. One question, two, that you will most definitely be able to answer by the end of this session is what is the purpose, likewise, what is the value of two-dimensional motion analysis in sport and exercise biomechanics. I had to trim out a few words there just to keep it up the text on the slide, but you get my point. Basically, why do we use this technique and for what purpose? Why do we use this technique and what do we get out of it would be a better way of phrasing it, essentially. And that is what you'll be able to answer, hopefully, at least by the end of this session. So let's start with the basic motion analysis model. And I've simplified this a bit just to keep things nice and simple to get things started. And this is somewhat familiar to what you may have seen in level 4 during the science and sport module. And in that there is a cyclical model in this case with motion analysis that begins with an observation. This may be of an athlete's performance. This may be of a particular motion, so someone performing an exercise and you want to assess their technique. This may be someone's technique, whatever the case may be. You begin with the observation, and this is where the 2D motion analysis comes in. From there we collect data which is then evaluated and either written up in a report or used to provide an intervention. Now this intervention may be a strength and conditioning based intervention, perhaps squatting on a Swiss ball. I'm not sure I'd recommend that for anything ever, but it could also be perhaps providing some sort of gait retraining for someone that's perhaps suffered an injury that needs to recondition themselves to a particular gait pattern, or it could be tweaking their technique somehow. But in order to assess the efficacy of your intervention, you will need, of course, to provide or perform a subsequent observation now after an appropriate period of time to see if it's been effective, and then the process begins again. Now when it comes to the data that we get out of this, it really is like connecting the dots. If you think back to your childhood, maybe this was a bit before your time, but connect the dot puzzles. If you can connect the dots on anything, then you can begin to perform a 2D motion analysis. This is done in the analysis software, which will be demonstrated to you during your practical session. That's not what we're going to cover here as to how you specifically go through this process, but this is what we have to do. Now, we measure the movement of specific limb segments around their respective joint or joints by applying retroreflective markers. That's this little ball that we see here, this silver sphere, to specific locations. And in the case of our runner that we have here, we may wish to apply them to these locations. So we have one on each knee. We'll just keep the terminology simple, straightforward for now. One on the ankle, one on the forefoot, one on the rear foot here, and again on the forefoot here. And essentially what we do from there is, as I say, connect the dots. But by doing so, these markers have now provided an indication for the axis of rotation, that is to say where the joint exists between the articulation of the two, or I'll say two, the bones that are within the limbs that we're looking at. And we are then able to measure the movement of limb segments around each other. So for example, between this marker and this marker, we've created the right foot segment. From the ankle marker up to the knee, we've created the lower leg, or the shank. And if we imagine that after this knee marker there's a hip marker somewhere up here, then we've got the thigh. And likewise here on the other side. So really what we're looking to do is take the athlete out of the analysis. I say that a bit tongue-in-cheek. We're not trying to completely remove them from the analysis, but we just want to look at their movement. Everything else, if I just pop them back in, is really just background noise and information that we're not interested in. So for example, the sorts of shoes they've got on, whatever's going on in the background, the fact that their laces are swinging around the place, what sort of socks they have on. This is all just background noise, as I say. It's not information that helps us determine the movement of their lower limbs. So the idea is we record the movement of our athlete with the markers attached. We apply our markers, obviously beforehand. Once we have the data, we connect the dots, and from that we create what is called a free body diagram. And biomechanists, as I'm sure you know by now, like to take basic topics and give them unnecessarily convoluted terms, and in this case it's absolutely no different. So here we have what I would call a stick figure, and I still do, just out of rebellion for the jargon that sometimes gets used, but in biomechanics circles this would be called a free body diagram. So if we look at this marker here, which is our ankle marker for the right limb, I believe, then we can measure the movement of this segment here around this point, so moving in this case clockwise. So this motion would be plantar flexion. On the swing limb here we have dorsiflexion, so the foot is moving in the opposite direction. Likewise here we can measure knee flexion here again in the swing phase, and knee extension in the stance phase. So it just depends on the direction that the movement's occurring as to what the motion is. So these markers, just to come back to them very quickly, the purpose of them, they're called retroreflective markers because hopefully they will reflect light better and will stand out more on your video recording than anything else in the recorded field of view. If you do happen to have anything that stands out the same or more, and this is very common on running shoes these days, you have those little reflective patches to stop your feet getting run over in the dark, and we very often have to put tape over those because they get in the way of our markers. But the idea is that in 2D motion analysis, these markers will reflect light in the visible spectrum as well as, or hopefully better than, anything else that we've recorded. With 3-dimensional motion analysis, we use infrared light, and they will reflect infrared light better than anything else we have in the room. And if there is anything else in the room that reflects infrared light better, say a mirror, then you need to cover it up or remove it, or perhaps perform the movement somewhere else, whatever it may be. By the end of it, you hope to only see these markers moving around, and from there create the segments, the limb segments, I should say. So an individual marker on its own, an individual retroreflective marker, is typically used as a passive joint marker. We'll come on to this later on in more detail. So really they're defining the position of the specific joint segment, acting as a reference point for where the axis of rotation is, but not really measuring the movement itself. An exception here would be this forefoot marker. There's no movement occurring around this forefoot marker. That's simply there so that we can create ourselves a foot segment. We do use, and you'll learn more about this if you go for level 6 biomechanics, we do use what are known as cluster markers. This is where we have 4 retroreflective markers on a single thin pad that's attached around a joint segment, usually the lower leg or the thigh, which are there solely to track movement. They're not there to define where the limb is, they're not there to define where the joint is, they're simply there to record the movement around them. But anyway, that's something we'll touch on more at level 6. For the time being, we use them as passive joint markers for the most part. So if you think back, way back to level 4 biomechanics, specifically your lecture on angular motion, you may just about recall a term or terms called relative and absolute joint angles. And these are 2 ways of measuring a joint angle in the human body when performing a motion analysis. So a relative joint angle is an angle that is produced due to the respective movement of 2 limb segments, and therefore either segment can contribute to the angle that is produced. An absolute joint angle is where you have a single limb segment which moves about a fixed vertical or horizontal line that does not move. It is, as I say, fixed. It is immovable. So let's look at a couple of examples. So here, instead of our retroreflective markers, we have these black circles here, but they represent the same thing. It's the same principle. So if we'll keep the terminology basic for now, we just have a marker up here on the shoulder, one on the elbow, one on the wrist. Then the 2 lines that we've created produce our elbow flexion angle. So the Greek letter theta here used to represent the word angle, and as the text suggests, this is a relative joint angle. So movement of the upper arm or the forearm can alter the value that you get here. Likewise, we have the knee angle here, which is a relative angle created by this marker that's been placed on the hip, on the knee, and on the ankle. So we have the shank down here and the thigh here between these 2 markers, and the relative angle that we have here determines our knee flexion angle. Now it's important to point out that most joint angles that you measure or are able to measure can be measured relatively or absolutely. So for example, in the case of knee flexion here, we can measure, or we can apply the same markers but have a fixed absolute line that is a continuation of the line created between the hip and knee marker, and measure the angle that is between the shank and this fixed line. So you may refer to this as a semi-relative or semi-absolute joint angle. So instead of measuring the obtuse angle here, we're measuring the acute angle that's produced here between this imaginary line. So moving on to absolute joint angles then. The example we have here is the hip marker, knee marker, and a fixed horizontal, what am I saying, line, and in this case we are measuring the angle that is produced here. Now typically we measure hip flexion extension by a vertical line acting down from the hip marker, acting vertically down, and measure the angle from the thigh segment that we've produced and this vertical downwards line. But it depends on the type of analysis that you're performing. And we'll look at some more examples as we go on. This is just to give you a general idea of relative and absolute joint angles. So, as we've said, we are able to collect a great range of data from 2D motion analysis. The one that we've just touched on joint angle measurements would give us the joint angle, and if we measure the movement of that limb, whether it's relative or an absolute joint angle, we're able to get angular displacement. Divide that by the time that it takes for that to occur, and you'll have angular velocity. Divide that angular velocity by the time and you'll get angular acceleration and so on. But of course, no movement really falls into either the linear or angular category unless you're performing it in a vacuum or in space, I suppose. If, for example, you were to, I don't know, I happen to have a pen in my hand, so I'll use a pen as an example. If you threw a pen across a room, it would move in both a linear and angular direction. It would spin through the air whilst moving in the direction that you threw it. So we can also measure the linear displacement and linear velocity and linear acceleration and so on. But we're also able to get a third type of measurement known as spatiotemporal. And again, biomechanists, confusing terminology used to represent fairly straightforward terms, or concepts I should say. Spatio refers to space, temporal referring to time, space and time, movement through space and time. So, I mean, in physics terms, space and time being the same thing, but I digress. Anyway, so this would include measurements such as step length, stride length, and cadence, so number of steps per minute, for example. So this just gives you an idea of some of the data that we're able to collect from this. Also contact time when analysing a running gait, someone's running gait, performing a running gait analysis, is another spatiotemporal parameter. Contact time being the amount of time that the stance limb is in contact with the ground for. So this convention that you see here, again, biomechanists, we like to make things confusing. We like to mix it up. And we have our own special way of measuring joint angles. Typically, when you think of measuring angular motion, perhaps if you think back to GCSE maths or something like that, if we begin here with this horizontal line, this is at 0 degrees as our starting position, and we're moving counterclockwise. Once we get to here, we have moved 90 degrees, 180, 270, and back to the beginning, 360. Well, biomechanists, that's not that straightforward. I will explain why. From our start position, if we go counterclockwise to this point here, we have 90 degrees as before, positive 90 degrees, and I move another 90 degrees and we get to positive 180. However, if from our starting position we move clockwise, then a 90 degree motion will be assigned a negative sign in front of it, minus 90 degrees. And another 90 degrees round will take us to negative 180 degrees. And the reason for this, whilst you may think, oh, that's just confusing, it's why would they do this? Why is biomechanics so difficult? Well, it does make sense when you think about joint motion. The greatest joint motion that you can produce, unless you're hypermobile, of course, but typically is going to be 180 degrees. So the shoulder is where you will see the greatest range of motion. So we can produce 180 degrees of flexion in a healthy shoulder, and likewise 180 degrees of abduction, again, if everything is all well and good with the shoulder. However, we don't have a joint in our body that's going to rotate any further than that, so there's no need. We don't need this standard convention. And so we can assign movement to either a positive or negative value. So we could say that flexion is going to be represented as a positive value, and the extension of a joint will be negative. Just hypothetically, just as a get started. Now, some of you might be thinking, well, hang on, I can circumduct my shoulder and my hip, and that movement is more or less moving in a full circle, and it's kind of you'd have to be very mobile to produce a perfect circular motion, but circumduction is made up of a combination of flexion, abduction and rotation, so we can break down these component movements and they will be within 180 degrees. So there we are. So let me give you an example. This is a bit of an advanced example. Again, this is more at level 6, but it's just so that you get an idea of where we're going with this. So if you start at the top here, we have the gait cycle, which you should be familiar with. So the gait cycle, 60% roughly represents where the foot is in contact with the floor, and here we're looking at this person's right limb. So the one highlighted in orange, you can see all the terminology down here associated with each specific phase, and the remaining 40% is where the limb is off the ground in the swing phase. So I've tried to line this up as well as I can. Don't know if I've done it perfectly, but the difference between the stance and the swing phase is represented by these lines here, these vertical lines. So to the left we have stance, to the right we have swing. And this graph, we have 0 degrees here, up to positive 30, and all the way down to negative 30. And this is based on ankle joint motion, and specifically movement of the foot about the ankle joint. And in this instance, dorsiflexion, which is flexion of the ankle, is represented by positive value. Plantar flexion, which is extension of the ankle, is represented as a negative value. So if we look at this grey line here, this represents the average from a very large sample population. I can't remember how many off the top of my head, but if you were to draw a thin black line in the middle of this grey line, that would be the mean value of this sample population. So it's a comparator. These two lines we'll come on to in a moment. So usually when your foot contacts the ground, typically we start in a neutral or slightly extended, or I should say plantar flexed position. However, anywhere within this grey line is considered normal. So if you start with a flexed ankle or a more extended ankle, then that's fine as long as it's within these values here. It then shifts into plantar flexion. This is at this point here in the stance phase. This would be from the initial contact through the contact response to the loading response phase. This is where the foot is on the ground, immobile itself, and this represents, the stance phase at least, represents the movement of the shank, the lower leg, over a fixed foot. So as the body moves forward over that stance limb, we produce this first small dip here into plantar flexion, so the ankle becomes more extended, and then very quickly it moves into dorsiflexion. That stretches out the calf muscles, the gastrocnemius. Oh, need to have another coffee. Gastrocnemius and soleus, and we increase our dorsiflexion angle here. So this is increasing the flexion of the limb. So that's all the way from this point here, which I suppose is more or less contact response, all the way here to the period of double limb support and heel off. And then the limb rapidly moves into extension, moving from the stance phase into the swing phase. So this is when all the potential energy that's stored up from those stretched calf muscles and the Achilles tendon is released to propel you forwards. And from that moment on, the foot is pointing downwards, you're plantar flexing, so you don't want to trip over anything whilst your foot is moving through the swing phase, so we need to get it off the ground, so we move it through the swing phase and up into a flexed position to lift the toes and lift the foot off the floor and reduce the chances of tripping. So here, on the left hand side of this vertical line here, during the stance phase, we measure the motion of the shank over the fixed foot, whereas in the swing phase we have a true relative joint angle. So movement of either the lower leg or the foot will determine this angle, although we tend to think of this movement as movement of the foot over the ankle, and on the left hand side movement of the lower leg over the ankle. But there we go. Like I say, you won't need to produce a graph this complicated at this time. They're coming, rest assured they're coming, but you need to get started first. These two lines here, by the way, this red and blue line, this is the average of a participant whose data I collected some time ago. I always think that red should be right. That makes sense, doesn't it? The red line should be the right limb, R and R. However, annoyingly, this is from our 3D software, by the way, the 3D motion analysis software, our Qualysis software. The red line represents the left limb, and the blue line is the right. Madness, I say. But there we are. What can you do? And the main finding here is this, well, I don't know how to phrase it, this severe reduction in dorsiflexion throughout the stance phase, and this excess plantar flexion through the swing phase. So this is indicative of someone with restrictions in the calf musculature. Could be other factors as well, but in this case, it was supremely tight calf muscles. I believe this person had a contracture, but I wouldn't swear to it. I can't remember off the top of my head exactly. So, let us move on. Let's consider the two different motion analysis techniques that we have in sport and exercise biomechanics, and those being the two-dimensional motion analysis and the three-dimensional motion analysis. So the 3D system you've undoubtedly seen in the lab, and it's somewhat similar to what we have here. Ours is is up on a rail. We do have these large tripods, but where there's tripods, there's things that people can kick over, and they're far better if the cameras are mounted up on a railing system. We used to have them on, as I say, whilst the railing system was being fitted, we had them on a tripod, but that just used to make me anxious whenever I delivered a session. Here we have multiple cameras. There's 1, 2, 3, possibly 4. This one seems to be pointing somewhere else there. 5, 6, 7, and there's one here. So there's 8. 8 cameras focused on a single area. With 2D motion analysis, we can use up to, or as few rather, as one camera. You may wish to use 2, but generally 1 or 2. We have 2, but we tend to use just the 1. So that's a practical difference. But what does that mean? What is the value of that information? Well, it really comes down to the planes of motion that we wish to measure our movement in. And I encourage you to watch these animations. I'll be silent in a moment, and then if you wish you can pause and see if you can recall, this is a bit of a test of some level 4 knowledge, what plane of motion each of these 3 movements is occurring in, and bonus points if you can tell me some of the muscles that are producing these movements. Okay, so starting with the image on the left, we'll keep them spinning, or keep them going, but I don't think I can turn them off. So we have rotation of the neck, shaking your head in disbelief of the awesomeness of biomechanics, no doubt. And this motion is occurring in the transverse plane. And the muscles that we see here are the trapezius, just here in the background, going green there. And in the front here, from the base, just bring it around here, the occipital part of the skull down to the manubrium and the clavicle, we have the sternocleidomastoid. You can palpate this muscle, you can feel it if you rotate your head left and right. You can see and feel this muscle engaging as you perform that movement. In the middle here we have a combination of abduction, adduction. So adduction, as it comes towards, abduction as the limb moves away, and this is in the frontal plane, as we know. So we have the hip abductors here, or 2 of them, the gluteus medius. I think the minimus is under there, but you can't necessarily see it. This is 2 of our abductors, and our adductors, which are primarily our groin muscles. We have the pectineus muscle here, this rather small muscle here. And I think this is meant to be 2 muscles merged into one. I think this, I think it's the adductor brevis and longus, put sort of represented together. I can't quite tell. It kind of looks like there's times like it. Anyway, I digress. I'm fairly certain it is. It can't be the magnus. Anyway, and this very long muscle here which is the longest muscle, coincidentally, in your body, is the Sartorius, which is a weak adductor, but it certainly plays a role. On the right hand side here, our third and final image, we see elbow flexion and extension. So there's flexion and there's extension. Glorious. So flexion, biceps brachii, brachialis, the brachioradialis here, the longer forearm muscle, and the smaller muscle here, pronator teres, which is a very weak elbow flexor, but it supposedly does contribute towards flexion, but it's really a pronator, as the name suggests. And on the other side we have elbow extension, primarily the triceps brachii and the ridiculously small anconeus, which you can't quite see. But again, 4 flexor muscles, 1 really extensor muscle. Why is that? Because gravity is our main extensor. But as ever, I digress. This, of course, occurs in the sagittal plane. This is typically where we see our larger ranges of motion. Admittedly, as I say, we shoulder abduction is one of the largest motions we produce, but overall we tend to see larger movements in the sagittal plane collectively when all things are accounted for. So knee abduction, for example, is a tiny movement. So something to actually to consider in advance, just whilst you're perhaps thinking about your data collection. The harder movements are going to be the ones that are smaller movements to assess. So larger movements, it's going to be easier. So maybe consider the sagittal plane as a starting point, or measure both. Anyway, I'm digressing terribly today. Goodness me. So we have our planes of motion, as we know.